Hello again and welcome to another review session for your Calculus 3208 final, brought to you by CDLI. And today we're looking at some more applications of differentiation, and specifically we're going to talk about how to use calculus to sketch graphs of rational functions. So these are a little bit more complicated than polynomials, but nothing we can't handle, I'm sure. So let's get started. A couple of key features we're going to look at here are determining all the important features of the graph, and then how do we take that and make an accurate sketch. Okie doke. So here we go. The things that we have to find when we're going to try to sketch a graph of a rational function. As always, we need a y-intercept that we get by letting x equal 0, and then we need an x-intercept that we get by letting y equal 0, and then we need horizontal, vertical, and oblique. Somehow I put an extra u in that one, and oblique or slant asymptotes. And we have all kinds of rules for those, and the rules that we had for those are from way back when we did a previous unit in limits. So all those things we have to remember now. This is a really interesting topic because it kind of brings all these different worlds together from all the stuff we studied in this course. Then we're going to look at how we get our maximum and minimum points, and that's basically the same method that we used for polynomials. We have to find our critical values. We use those to get our critical points, and then we got to get our y values from the original function, and those are what tell us the other coordinate for our critical points. Intervals of increase and decrease, we look at intervals using the first derivative. Inflection points, we have to find our hypercritical values, so these are our HCVs, and we also have to get their y values. And intervals of concavity, we use a second derivative to test some intervals. Okay? So first derivative to test for intervals of increase, decrease, and second derivative to test for concavity, as always. All right, let's get down to the important business. Here's an example. Now, this is a very typical type of thing to do with this type of a question, especially if this were on a test or an exam. Notice that we give you the original rational function here, but also the equations for its derivative and its second derivative, because this type of problem takes a long time to do typically, and if you have to spend more time differentiating and simplifying the derivatives, well, that just makes it almost impossible to finish in the required parameters. So what we do is we typically give you the derivatives for these things on this type of question. All right, so let's get started. Y-intercept. To get our y-intercept, we have to let x equal 0. So if x equals 0 here, then what we're going to have is f of 0, which will be 0 over 0 minus 1 squared, and that's 0. So we have a y-intercept at the origin. So that means that's also going to be an x-intercept. There may be others. We'll find out in a second. So let's check. Our x-intercepts we find, as always, by letting y equal 0. So if we let y equal 0 here, what are we going to come up with? Well, let's see. If y equals 0, we have 0 equals x over x minus 1 squared. And there's no way this stuff can make a fraction equal 0. It's the denominator, so it has to be up here. And the only place that works is when x is equal to 0. So if x equals 0, that's our only x-intercept. So we've got both intercepts in one point. That's nice to have that taken care of. Okay. Now, let's go after some stuff that deals with the first derivative. So all the first derivative business, let's take care of that next. We've got to find, oh, sorry, I forgot about my asymptotes. Righto. So let's get those asymptotes worked out. Vertical asymptotes, well, how do we find those? If you remember from a previous unit, we look at the original function f of x, and we determine places where the function is undefined. So basically, where are there factors that make the denominator equal 0, but they're factors that don't cancel out with anything from the numerator. Those wouldn't give us vertical asymptotes. They would give us points of discontinuity or removable discontinuities. So in this case, I can see that if my denominator equals 0, the only way for that to happen is if x is equal to 1. So I've got a vertical asymptote at x equals 1. Horizontal asymptote, well, we sometimes have them, we sometimes don't. The trick for those is to look at your original function and check the degree. So we look at the exponent on top, the highest one we have there is a 1, and down the bottom we have a 1 here, but that whole thing is of course squared because of that, which means we've got degree 1 over degree 2, so we will have a horizontal asymptote. So that'll be at y equals the limit as x approaches, and it doesn't matter specifically for a polynomial whether we go plus or minus infinity. It'll give us the same limit, sorry, for a rational function that's only polynomial numerator and denominator, I should say. So that's going to give us x over x minus 1 squared, and since the degree of the numerator is less than that of the denominator, as we saw before, that limit equals 0, so our horizontal asymptote is along the x-axis. Okay, so we've got that. Next, we're going to look at the derivative stuff. Sorry for getting ahead of myself earlier. All right, so let's get those derivative things worked out now. So we'll get some space here. So we have our first derivative, and we want to find out what are our maximum min values, where are we increasing or decreasing, and of course, all of that stuff is contingent on our critical values. So we get critical values by looking at where the first derivative equals 0. So if the first derivative is equal to 0, then we're going to have 0 equals negative x plus 1 divided by x minus 1 cubed. This part can't make it 0, as we know, so we're just going to have 0 equals the negative of x plus 1. And very quickly solving that, we get that x equals negative 1. So we're going to have a critical value at x equals negative 1, where the derivative is equal to 0, and that could give us a maximum or a minimum or something close to it. We'll have to wait and see. But remember, now we're dealing with rational functions and not just polynomials. We also have to look at where the derivative f prime is undefined as well. So where is our derivative undefined? Well, the way that our derivative will be undefined, in this case, the only way I can see is if that denominator is going to be 0. So if 0 equals x minus 1 cubed, then x would have to be equal to 1. Now, what does that mean? Well, that's definitely a critical value because the derivative is undefined, but it cannot be what we call a critical point. If you recall, the definition of a critical point says you have to be a critical value and the function has to be continuous. We have a vertical asymptote at x equals 1. So it is a critical value because it's possible we may change from increasing to decreasing or vice versa, but it's not really a critical point. It's just a possible change in that increasing, decreasing behavior. So we do have to check our number line for intervals of increase and decrease, counting both negative and positive 1 as critical values, but we will not get a max or a min value at x equals 1 because it's an asymptote. All right, so let's do a number line check here with our first derivative and find out what's happening at those critical values. So we've got a negative 1 and a positive 1 as our critical values, and we're going to have to look at what happens with f prime and what that means for the graph of f. Okay, so for f prime, what I have to do is plug in some numbers in those intervals that we're talking about. So let's say we take a number like negative 2 and plug that into our first derivative up here. And I'm going to get a negative of a negative on top over a negative cubed on the bottom. Okay, so that's going to give me a negative of a negative over a negative, which I think is going to be a negative. Wow, that's a lot of negatives. So that tells me that we're going to be decreasing until we get to x equals negative 1. All right, so let's get rid of all that foolishness that I scribbled down there, and we'll see if we can figure out something on our next interval. At, let's say, x equals 0 being a good point to check in that one. So if we check at x equals 0 for our first derivative, we're going to have 0 plus 1 on top, so that's just a 1. Remember, there's a negative out in front of this business. And then in the denominator, I'm going to have negative 1 cubed. So this is going to give me 1 over a negative, and then make that negative, which I think turns out to be positive. So our original function is going to be increasing on that interval. All right, so we've got one further interval to check. And the last interval that we have to check here is going to be from positive 1 on to infinity. Uh-oh, it looks like I erased my number line. Let's just put that back. Okay. So we've got to go from positive 1 on to positive infinity for that interval. So let's check a good point in there, like, I don't know, x equals 2 should be fine. So our numerator for our derivative will give us 3. Our denominator will give us 1 squared, which is 1. Then the whole thing is going to be made negative by that negative sign out front. So we're going to be a negative first derivative, which means the graph is decreasing on that interval. Okay, so we know that our function is going to be increasing on the interval that goes from negative 1 up to 1, and we're going to be decreasing on 2 separate intervals. So we'll write those with a union in our notation. So we're going to go negative infinity up to -1, and then we have to say union with +1 onto positive infinity for our decreasing behavior. Okay, the only thing we don't know now is what is, at -1 we can see that this is going to be a minimum value because we decrease and then increase. So this is a local minimum. We don't know the y-coordinate, so we're going to have to figure that out. So at -1, I'll plug that into my original equation, and that will be f of -1, and that'll be -1 over -2 squared, so that's -1/4. So at -1/4, that's going to be a tough one to plot on a graph. We have our y-coordinate. Okay, let's clean all this slide up now, and then we'll try to figure out stuff about concavity and inflection. So let's get rid of all that space junk. And for concavity and inflection now, we're going to have to look at our second derivative. And so remember, for hypercritical values, for a rational function, we have to see where we're equal to 0 first for f double prime. So we want that, but we're also going to have to find out where f double prime is undefined. Alrighty. So let's find out where it's equal to 0. 0 equals 2 outside of x and 2 divided by x minus 1 to the power of 4. So if I do that, what I have is this stuff. Never going to make me 0. I only get x equals -2. So my only possible inflection point is going to be at -2 as a point, because that's my only true hypercritical point. But I can get other hypercritical values if my second derivative is undefined. And that'll only be undefined when this denominator is equal to 0. So at x minus 1 to the power of 4 being equal to 0, we get x equals 1. Now again, that's our vertical asymptote one more time, which means we're going to have to check for changing concavity at that point. However, it cannot be an inflection point technically because it's not really a point on our graph. So let's check a number line for all this business now. And we've got 2 points to plot. We've got a -2 and a +1. And then we're going to check our intervals for this stuff using our second derivative, f prime prime, and see what the behavior of f is. So for the second derivative, f double prime here, let's see. At x equals -3 would be a good point to check in that interval. So f double prime at -3 is going to be equal to, let's see, a 2 outside of -1. So I get a negative numerator. And my denominator here is always going to be positive. You'll notice the second derivative is power 4. So even exponent means it's always positive. So this is going to be negative over positive, which is negative. So our original function is very sad and concave down out there. Now, in the second interval we have from -2 up to 1, we can test that at 0. So let's test it at 0. So we want to figure out what's the story with f double prime of 0 here. And that will be f prime prime at 0. And that's going to be 2 times 2 divided by -1 to the power of 4. And that's a positive number. And for our last interval there, we'll check out what's going on at x equals +2, say. So at +2 now, we're going to have f prime prime at 2. And that shall be 2 times 4 divided by 1 to the power of 4. And that's positive again. So we can see that we were concave up on the next interval. Yay! And our concavity didn't change at the asymptote. We're going to be sort of bent upward again on the other side of it. So we did have to check that out. By rule, it is a hypercritical value, but we didn't get any change in concavity, so that's not a big deal. So we're going to be concave up for this function on an interval that starts at x belongs to. Concave up will start at -2, and it's going to go on all the way up to +1, and then it's going to skip over 1 because the second derivative doesn't exist there. It's going to start at 1 again on the other side and go on to positive infinity. So we just skip the asymptote starting at -2. And we're going to be concave down everything from -infinity all the way up to -2. Okay, the only thing we don't know is the y-coordinate at that special inflection point. So we need to find f of -2. So I'm just going to scribble that in this space because it doesn't take much time to do that. So we want f of -2, and that's going to be -2 divided by -3 squared, so -2/9. Not a very big number. So -2/9 is the y-coordinate of our inflection point. Okay, so there's all the gory details. in my massive hand scratch handwriting. And here they are in much neater form when I pre-type them to make them a little bit cooler. And now we just plot all the points and see if we can figure out what the graph has to look like. So x and y intercept is the same point. We only have one for x, and it's our y-intercept at 0. We have a vertical asymptote at x equals 1. So this is one of those cases of do as I say, not as I do, because I'm being consistent with your textbook and making my vertical asymptote a solid line, but I'm going to make that solid line be that funny blue color that they use to represent asymptotes. That's okay, I suppose. And we have a horizontal asymptote at y equals 0, so that's right along the x-axis. There's our horizontal asymptote. And then we have to plot our critical points, and we only had one of those, -1 and -1/4. So this is a scale of, looks like 2 units to a block. So -1/4 is going to be way down here. I'm going to exaggerate that. That's probably a little farther than it's supposed to be, but I'm exaggerating a little bit to make it clearer for you. And our inflection point was at -2 and -0.22. So just ever so little bit above where that critical point was. So what I have to do is I have to draw a graph that has a minimum value right here. It has no maximum values, and we have to approach this asymptote, this vertical asymptote right here. We have to approach that. So I'm going to say we have to inflect concavity at -2. So it's probably the best I'm going to be able to do with that. But we have to have a minimum value right there, and then go through this intercept, and then approach that, maintaining the fact that we're increasing on that interval and concave up. So the one thing I'm not very happy about is how this turned out over here. So we should be concave up there, but decreasing toward. That's a tough bit to draw because it's pretty fine motor skills that I probably don't have. Then to the right of that asymptote, well, which side of the horizontal asymptote do we draw on? We did determine that we were concave up on that interval and that we were decreasing on the interval that's out beyond there. So that means it's probably going to have to be out here. And so there's a good rough sketch of what our graph should look like. Okay? So that's how we graph rational functions using all the nuts and bolts of calculus. And let's jump on. Here's the your turn question, which is a very similar question to the one that we just did. So if you want to pause the video, take some time to work all that out, go for it. And then here's the solution, or basically this is how you find all that information. It's a little bit cluttered there, but we've got to fit it all on so it's easier for you to have it all in one spot. I figured was better. And that's all the details there, but take some time to pick through that if you want. And then here's the graph that we come up with, something similar to what we had for our graph on the last one. And with that graph, all the details are repeated over here on the right to make it a little bit easier for you to see what's happening. And let's just highlight some of the key features of the stuff that we looked at in this section. So some of our key features were, we said that we find our x and y intercepts the same way as always. No need to talk about that again. Find all of our asymptotes just like we did in our previous unit with limits. Maximum, minimum points, increase, decrease, inflection, concavity, all those things here work exactly the same way they do with polynomials, with one important exception, and we can't forget that. We've got to remember that critical values and our hypercritical values as well can both be found watching out for when f prime is undefined as well as when it's 0. And for the hypercritical values, we've got to check for when f double prime is undefined as well as when it's 0. Okay? So that's graphing rational functions in a nutshell. Hope it was helpful. Hope your studying is going well. And if you have any questions, post them online. And happy studying.